So let's finish this off. The last step is to calculate all of our power values. And the process is exactly the same, moving from our voltage triangle over to our power triangle as it was when we moved from the impedance triangle to the voltage triangle. Okay, the difference, of course, now this transference was using Ohm's law, and now we'll use the power equation to move forward. So what is power equal? Do I have a spot to squeeze this in here? P equals E times I, right? Voltage times current equals power. So all we have to do is make sure that we're calculating for the right kind of power using the right kind of voltage, okay? Which means we're just matching the vectors. Okay, the vector here at 0 degrees, which represents the voltage drop across the resistor, is going to be used to calculate our true power. Our power vector here also at 0 degrees. So ER 30.7 volts multiplied by I 3.07 amps will give us the true power here in our circuit, which is 94.25, and what's the units for true power? Watts. Okay, so there's the true power. That's the actual work that is done by our circuit. Next, let's look at the hypotenuse, which is our total, all of our total values in our circuit. So our applied voltage was 120 volts multiplied by 3.07 amps will give us our apparent power, which is 368.4. What? What's the units for this? Volt amps. Those are our volt amps. So our watts, the power that we actually use, the work being done by the circuit. Okay, apparent power in volt amps, that is the demand on the power supply. Okay, the amount of power that we get billed for at the end of the month. So we can see it's not a very efficient circuit, is it? We're spending a lot of money on power for doing a considerably smaller amount of work. Okay, rest of the powers, more of the same. The reactive power at the inductor, 46.97 volts, multiplied by, right here, 3.07 amps. Okay, volts times amps gives us 144.2 VARs. VARs, volts, amps, reactive. Same thing down here for the capacitive VARs, 162.87 volts, multiplied by our current, gives us, and I'm going to round this to 500, and again, VARs. Same units, right? Volts, amps, reactive. VARs. We don't even need to calculate this number. Okay, it doesn't matter. All right, we didn't need it to find any other values. We don't need it anymore to calculate anything. We've got most of our numbers at this point. We're never asked for it in our question, so we don't even have to calculate it. If anyone did, I've got 355.8 is the number I calculated. Hopefully you got the same number. But at this point, we don't even need it. Okay? The only thing left to consider is what is the angle of our triangles and what is our power factor. So the angle, we can use virtually any method you want. Okay? We could use sine or cos or tan, and we could use any one of the triangles. All right? I would suggest that as we moved along, we had more drift in our possible rounding error. So I'm going to go all the way back to the beginning, and I'm definitely going to use R because that was a number that was given. That wasn't calculated at all. All right? And then I could use X, and that would be my adjacent and my opposite, which means the function I would be using is tan. Or I could use Z, and now I'm using the adjacent and the hypotenuse, which means I'm using cos. Okay? Doesn't matter. Again, you can pick whatever method you want to get there. Did I write that number down somewhere? Oh, I thought I did. Now I don't even see it. Ah, there it is right there. 75. 75 degrees. Okay, so we can see that even though I put some effort into drawing this more to scale, I still didn't get far enough, did I? This is a really, really large angle, and we see that when we compare our hypotenuse at 39 ohms and our opposite at almost 38 ohms. Okay, this is a huge angle. All right, this is a really, and we looked at it here when we compared our powers, this is a really, really terrible circuit, quite frankly, because when you calculate the power factor equals, and remember, it could be this number over this number, okay, the adjacent over the hypotenuse, true power over apparent power. Adjacent over hypotenuse could be the voltage drop across the resistor over the power supply. It could be the resistance over the impedance, okay, or it could be what the adjacent over the hypotenuse is, which is the coast of the angle. Okay, all kinds of different ways to get to the same place. The result is 0.2558. So in terms of carrying decimal places, I typically say 1 or 2. All right. When it comes to the power factor, the answer is at least 2. All right. Most of my exercise sheets will show you 4. That's why I wrote 4 here. I don't feel like you need to carry 4 decimal places, but you need to carry at least 2. Okay, 2 or 3 would be just fine. Okay, we're not quite done though. Power factor, 0.2558, what? Okay, well, it's not a unit per se, but it is one final descriptor about what's happening. Our circuit, because the resultant vector ends up pointing towards the capacitive portion of our vectors, means that we have a capacitive circuit. Okay, when we have a capacitive circuit, what's leading what? Okay, Eli the Iceman, which is where the whole conversation started in lesson 1, said that in a capacitive circuit we find the current leading the voltage, which is exactly what we want to say about our power factor, that it is leading. Okay, so our power factor is 0.2558 leading. Okay, and that sums it up. That's all of our numbers. Okay, I want you to spend some time working the exercise sheets doing that. I do have 1, possibly 2 more videos yet to come. Some more theory after all the numbers. I want you to spend a little bit more time getting comfortable with the numbers first. As you go through different exercises, you may or may not recognize a trend starting to evolve, and it might lead you to this next lesson. You might even see it coming. Okay? For now, though, I don't want you to carry on with my lessons. If there are more videos available to you, don't jump into them right away. Go to the exercise sheets, work on the math, gain a comfort level with this work.